Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. Having discussed numerical methods in the past, we now train our attention on modeling a vibratory system as a continuous system, wherein the mass and stiffness property is considered to be not discrete, but a continuous function of the spatial variable. Okay. And in that context, we will get started first with a very simple continuous system, and that is a stretched string. In the lecture, we will deliberate in detail as to how this continuous system differs from a discrete system, which is what we have been analyzing in the past. Okay, we now switch to the new topic of vibration analysis of continuous systems. So till now what we have been modeling any vibratory system as a set of discrete spring and mass. Okay. So typically an example is of an inertia or a disc which is mounted on the shaft, and if it is to be analyzed as a torsional vibratory system, what we have typically done is we consider this disc to be a lumped inertia, and the connecting shaft is treated as a spring element, right. So that is what we do. So essentially the shaft is considered massless and has only the property of storing the strain energy, which is signified or indicated through a torsional stiffness here. So this KT represents the shaft and the disc represents the inertia. So that way we model this system as either the single degree of freedom system, or if there are multiple discs, then as the number of discs increases, we can keep on adding inertias and the corresponding degrees of freedom. So the point here is the system is discretized and the mass properties are lumped at some definite discrete locations. Okay. For example, the location here is at a distance a from the fixed end, and the inertia is interconnected through the stiffness elements. The stiffness elements typically we treat them as massless, so inertia properties are associated with only disc in this particular example. Although one can consider the distributed mass in the shaft, and we can take care of the mass of the shaft. We know how that is done by updating our stiffness, updating our mass inertia, but that again is an approximation, right. So a typical system like this, when modeled in the form of some discrete lumped inertias, is called as the discrete system model or a lumped parameter model. Now that works very well in terms of the accuracy of the estimate of the dynamic properties, if this inertia which we are using to represent the inertia property is significantly large in comparison to the inertia or mass property of the shaft itself, and in that case we can definitely assume that the mass properties are associated with the disc, and the stiffness property is associated with the shaft, and that more or less works fine in giving reasonably accurate estimate. As I said, mostly when the disc properties or inertia properties of the disc are much larger in comparison to that of the shaft. However, in some cases this kind of a lumping may not be feasible or may lead to inaccurate results. For example, if I do not have a disk and if there is only a shaft here which is spinning, and then I am supposed to look at the torsional natural frequency of this shaft, I don't find any specific physical element here where I can lump the mass property. But I may also consider that this particular system is like a series of shaft element and inertia element like this, and we have seen couple of methods in the numerical method section, that you can easily consider this to be a set of several discrete segments. But again here we still are stuck with the discrete system model, wherein there is still going to be some approximation, because this particular part of the section will still be massless, and you are going to lump that inertia property at every discrete point in the entire continuum, right? So in such cases it is important for us to also look at an alternate way of modeling this vibratory system, particularly when this kind of a lumping is expected to generate inaccurate results, and if you are interested in the precise estimation of natural frequencies of the system. So in absence of this inertia, the system is broadly a distributed system, in the sense that the stiffness and mass, both of these properties, are distributed throughout the domain, starting from x equal to a to x equal to L, right. So there is a continuous distribution of this mass and stiffness property. So we have purposely kept ourselves focused on the discrete system analysis and not so much on the distributed system analysis. This discrete system approach or modeling approach is also called as a lumped parameter model, wherein the properties of the inertia are lumped at some finite number of degrees of freedom, and I mean the degrees of freedom are associated with those lumped elements. For example, here this lumped disk or a disk representing the lumped mass has an associated theta degree of freedom, and then if you have multiple of such disks, theta 1, theta 2, theta 3, up to how many number of disks that you have, you will have as many number of degrees of freedom, but the degrees of freedom are still going to be finite depending upon how you discretize your continuum. Okay, so this is basically a lumped parameter model. Now obviously the reason why we spend so much of time in this lumped parameter model is the very fact that helps us to have a manageable model of the system. So there are distinct advantage of this lumped parameter model, wherein we lump an otherwise continuously distributed mass and stiffness properties, we lump them at discrete positions. The governing equation of motion that we have obtained in many of the cases, like even for 2 degree of freedom, 3 degree of freedom system or multi degree of freedom system, the equation of motion is an ordinary differential equation of motion, second order ordinary differential equation of motion. So you basically get d2x1 by dx by dt square plus k1 or k1 plus k2 into x1 into plus or minus k into x2 equal to f of t, and those kind of ordinary differential equations we observed. Sometimes in fact many times for multi degree of freedom systems these equations were coupled, but essentially all the equations were an ordinary differential equation, which is a hallmark of the equation that governs the dynamics of such discrete system model or a lumped parameter model. But as I said, the main reason why we chose to model that system is that it is easy to model, because you have some discrete number of degrees of freedom, and so the number of equations are something which you can control by way of modeling the system, and many times it makes sense to practically get the model of the system manageable, simpler and easy to evaluate. That's the most important part. We can keep on complicating our model of the physical system and make it as complex as one can get, but then ultimately as engineer we are supposed to solve it to get the necessary response characteristic. Now if your equations of motion are intractable in terms of its response values, then making a system or model of that system very complex makes no sense. Okay, so as long as you don't compromise much on the accuracy of the estimate of the response, there is no point in making the system too complex. So most of the times all mechanical vibratory systems reasonably can be modeled through lumped parameter model, and the initial level estimates can easily be obtained. And then if the estimates vary from or deviate from the experimental observations, then you can refine the model and make it more updated and then solve it further. But as I said, in some cases like the second example that I have given you, apart from the various numerical methods, this is a fit case for modeling it as a continuous system. So a continuous system, also called as a distributed parameter model, because the mass and stiffness properties of this continua is continuously distributed as a function of the spatial variable. So that model is the continuous system, and obviously because if it is continuously distributed throughout its length, the mass and stiffness property, then obviously we will have the mass as a continuous function of the position variable x, and because you can have infinite such x positions, the degrees of freedom for each of the position, if you count, that will be obviously mathematically an infinite degree of freedom. So continuous systems are essentially an infinite degree of freedom model. More appropriately, I would prefer to call it as a distributed parameter model. Now what are the distinctive feature of this distributed parameter model? That m and k are continuous function of x. In this particular case, if x is the parameter defining the length, the equation of motion, as we will shortly see, the equation of motion will turn out to be partial differential equation, okay, not an ordinary differential equation. Solutions would be more accurate. Why? Because there is no approximation involved apart from some of the standard approximations, but there is no approximation in terms of how many segments I am going to discretize this. So the moment discretization happens, you are making an assumption. You are making an assumption that a 1 meter bar is going to be discretized into 10 segments, 20 segments, 30 segments, and then there is no scientific justification of segmenting it into 10 or 20 or 30 number of segments. Although you can carry out all your the analysis in terms of how many segments you can use, but then there is one can always say that I may not be able to get the nth natural frequency accurately, because it will be confined to certain number of frequencies. So that way this particular approach will yield most accurate solution. Okay. The flip side of it is the mathematical formulation and solution for practical system is complex, many times extremely difficult. Okay. So sometimes the continua may not be so simple, like a constant cross section bar or a beam, and the moment it deviates from that geometry of standard geometry, then formulating the governing equation of motion can be tough, and solution is even tougher. Okay, getting the solution becomes challenging, if not impossible. Okay, so there are of course various ways and methods people have done that part of obtaining appropriate solutions from the formulation, but the bottom line here is, if you want to have a quick and less accurate but approximate and workable solutions, it is the lumped parameter model which gives you quicker solution. And if you want to have a very accurate estimate or very accurate solution, then you have to use a distributed parameter model. But then in some cases it will be very challenging to get the solution, and modeling of course has its own challenges for systems which are complex in its geometry. Okay, what are the examples? Taut strings is one of the most basic continuous system, and that is what we are going to start with in analyzing the continuous system, just to give a flavor of what a continuous system is and how the governing equations are formulated and solved. So one of the basic and the most simplest of the continuous system is a string which is stretched. So it is a taut string. The examples are transmission wires which are pulled and fixed at their the supporting poles. So these transmission wires basically are constant diameter long wires, stretched and held at their ends. Now because of their own weight they get stretched, but they are essentially taut. The other more common example which you can relate with very quickly are the strings of the musical instruments, such as a guitar or a violin, where the ends of the strings are taut, and then they are fixed at both ends, and such taut strings then can lead to generation of sound when you pluck it. So these are basically some examples of a continuous system. So the simplest of the continuous system is a stretched string. That's what we are going to start with. A string is a long wire pulled at both the ends and with a constant tension P, right? So there are assumptions which we will declare right at the beginning, that the stretched string has cross sectional dimensions far smaller than the length of that string. The second assumption is, of course, that applies to all the vibratory system, but here small amplitude vibration. And when we talk about the small amplitude assumption, it means that the string is going to vibrate in the lateral direction with very little amplitude. So the slope change across a small distance is going to be very small. Okay, and the third one, as we discussed, that the vibration happens in only one plane, lateral vibration. The tension in the wire is constant. Okay, the fifth assumption typically is an important one, that the wire or the string does not offer any lateral stiffness. In the sense that if this string vibrates with this kind of a motion, it is not going to create a restoring force out of the lateral stiffness. It is essentially the tension P that is acting on the wire, okay, along the axis of the string. So these are some of these assumptions that we shall work in formulating the governing equation of motion for such a stretched string. Now because we are going to consider this as a distributed parameter system, which means that we are not going to lump any mass or stiffness along the length of the string. So all the properties are going to be a continuous function of the coordinate x, which is going to be along its axis. So in such cases, what we do is we consider a small a small element at a distance, let's say x, and that small infinitesimal element of length dx is going to be considered as an element under the action of variety of forces. So this small dx length, I can now write or show here that the string may have an arbitrary way in which it will get stretched or moved, and we are basically going to focus on its dynamics. Okay, so I am going to assume that this particular small element of length dx is considered in the plane of its vibration. So this basically is the direction, sorry, this is going to be direction x and this is going to be direction y along which it is going to vibrate. X is the actual coordinate of the string, and at a distance, any arbitrary distance x, we are chopping off this particular element of the string and looking at what are the forces which are going to act on it. So this is your yx plane in which it is vibrating. So we are basically ensuring that the vibration is only in xy plane, and this position of the string is x, and we are taking a small elemental length dx at distance of x. Now at this particular position, the string is vibrating in the xy plane. So the vibratory motion is defined by its vibration amplitude, which is going to be wx comma t. Now in the discrete system model, we always defined the response as x of t, which means that the motion of a particular degree of freedom or a particular mass element or inertia element is defined as the response as a function of only time. Okay, but here because this system is continuously distributed in x, we define the response not only as w as a function of time but also as a function of x, which actually means that the response at any location x along the length of the string at any particular instant of time is going to be wx comma t. So wx comma t is going to be its vibratory response, which is going to define the response at any spatial position x and at any time t. That's wx comma t for you. Now this response is going to be shown here as wx comma t, and this small element of the string is obviously going to be in equilibrium by the forces which are going to act on it. So the constant tension P which acts on this string is shown here. Now at this extreme end, the angle made by this force or the tension in the string is theta, and as the string vibrates at the other end at a distance dx from this particular point, the slope might change, and that small incremental change in the slope is d theta that I am going to define. Okay. Now I forgot to also mention here that the string itself will be subjected to external forces. As any vibratory system, we can define the force f of x comma t. So these are the forces which are external to the string, which are acting like distributed over the length of the string. So f of x comma t is basically the external force that is acting on it. So I am basically going to write this as a general forcing function f of x comma t. This is the force per unit distance, So the unit is important to note, that it is force per unit distance of the string. That's going to be the force which is going to act laterally on the string. Now what kind of the force which will act, like for example, if you consider the transmission cable, it could be the wind load, okay, which is going to act on the string. In very specific cases, it could be electromagnetic force, it can be drag forces on the vibrating strings. So these can take different forms, and so basically it represents a generic external force acting on the string. So this is what we are defining as f of x comma t. So now if you look at the force balance in this particular condition, I can write the vertical force balance along the y direction and apply the Newton's second law. So obviously our job will be to apply this Newton's second law here, which is going to be mass times the acceleration in the direction the forces, sum of all the forces which are acting on this elemental string. Now what are the how do you define the forces which are going to act on this elemental string? The vertical force at one end here is going to be it is going to be capital P, the tension in the wire, sine theta. That is basically the vertical force acting on this side, and on this side this is going to be P sine theta at x plus dx. Okay, so the vertical component of this pulling force or tension in the string at x as well as at x plus dx. Okay, so these are the two forces which are acting. Now the net force is going to be how much? P sine theta at x plus dx minus P sine theta, this is the force at x, plus f of x comma t, that is the external force acting on the string, times dx, because that is going to be the total force in the small elemental length dx. Okay, because this f of x comma t is the external force per unit distance. Okay, P is the tension, so the tension in the string is P. So now this has to be equal to the total the mass times inertia. Now the mass of the string is rho into dx, where rho is mass per unit length. So kg per meter. Okay, now this rho need not be a constant value, so let us write this more appropriately as rho of x dx. That means the material density may in fact can vary, so we are making it a very general case that this now becomes the mass per the total mass of the string element of length dx times dou to w x comma t, that is this is going to be the acceleration of that elemental string. Okay, so dou to w x comma t by dou t square, that's basically the acceleration of this string element. So if I write this in this form, dou to w, now I am going to skip x comma t. It is implicit that it being a partial derivative, it has to be a partial derivative because w is function of more than a variable or more than one variable. It is going to be function of both x and t. So the left hand side is mass times acceleration is sum of all these forces. Now p sine theta at x plus dx, that is this distance, is going to be, I can write this and expand this in Taylor series and can write this as p sine theta plus dou x of p sine theta dx. Okay, so this is almost like sine theta is at this particular position x plus dx is going to be sine theta plus d theta. Okay, so that's basically is going to be your p sine theta at x plus dx position minus, so this is entirely the first term that you have here, minus p sine theta is the vertical component of the force at x position, and then plus f of x comma t dx. That's your complete equation. Now this term cancels out, these two terms goes out of the equation, and then you are left with what, dou x of p. Now sine theta, this is another assumption that I am going to make, because the amplitude of vibration is small enough, the slopes are very small, and then sine theta can be approximated as tan theta, and tan theta is what, it is basically this angle, and that is basically going to be the incremental change in the response w with the position x. So that slope is going to be dou w by dou x, that is the slope at x equal at the position equal to x. So dou w by dou x is essentially is going to be sine theta term. So I can write this as dou w by dou x, and then this is p sine theta and times dx plus f of x comma t dx, and that on the left hand side remains as this. So finally I can write this governing equation with an assumption again, and that assumption is already made explicit, that p is constant. Okay, it's not going to change with the distance or position x, and therefore you can take the pulling force, the tension in the string, out of this particular derivative, and then I can write this as p dou 2w by dou x square dx plus f of x comma t dx, and on the left hand side remains the same. So now finally cancelling out dx throughout, I am basically left with this equation, rho of x dou 2w by dou t square plus, oh sorry, equal to p dou 2w by dou x square plus f of x comma t. That basically is your governing equation of motion of a stretched string, which is essentially treated here as a continuous system. Now it is worth noting down now the difference between the governing equation of motion of a discrete system model of a vibratory system. So we wrote that as mx double dot plus kx equal to 0. These derivatives with respect to time have been the ordinary differential ordinary derivatives, and so in lieu of that, in the continuous system what we get are the partial derivatives of the response variable w. So that is one of the major difference here in the continuous system, that in the governing equation of motion involves partial derivatives, obviously because the response is obtained as a continuous function of the spatial variable x. Now to get going, it is natural to now assume the way we have done in a discrete system case as well. In the initial phase, we for finding out the natural frequencies and mode shapes, we set the external force to 0 and then start solving the governing equation of motion for a free vibration case. And so obviously if we um, uh, if we get the external force out of the equation, this equation then turns out to be del 2 w dou 2 w by dou x square equal to, I can now write this as 1 over c square dou 2 w by dou t square. What I have done is I have taken p on the left side, and so this c is square root of p by rho. What is important to note that rho is mass per unit length. Okay, so it's not density as such, but it is mass per unit length, and so the units are important to be noted here. C is the wave speed, the speed with which the wave travels, and this equation represents the wave equation. Okay. Now, how do we solve this wave equation? There are methods, out of which the most common and simpler approach is to consider this w as a function of x and t, to be represented as a product of two independent quantities, each independent in a specific variable. So what I am basically going to write this wx comma t as a product of a function only in x and a function only in time. Okay, so this is an assumed solution for this wave equation, and if I use this assumed solution, I can substitute back into the original equation to get the first derivative on the left hand side to be capital T. I will drop the argument here, and because when I take the derivative of this, t being only function of time, the partial derivative now turns to ordinary derivative. So d2 x by dx square is equal to 1 over c square um, yeah, 1 over c square x d2 t by dt square. Okay, and I can rearrange this to write it in this way: c square upon x d2 x by dx square equal to 1 upon t d2 t over dt square, and that's how I get. Now you may notice that the left hand side part of this equation is only a function of x, because capital X is a function of x, whereas on the right hand side you have this term which is completely a function of time. So when these two functions are equal, we know that individually they are equal to a constant. Okay, so I can write this constant as a, and now start from here. Okay, so let me go to the next page, and I can write this c square by x d2 x by dx square equal to 1 over t d2 t upon dt square, and that constant I can take equal to minus omega square. It's a constant, and it is logical to assume that constant to be minus omega square. That basically generates one equation, which is going to be d2 t by dt square plus omega square capital T equal to 0, and if you take the first term, then you get the second equation, which is going to be c squared d2x by dx square equal to minus omega square x, okay, which basically can then turn out to be d2x by dx square plus omega over c capital X equal to 0. Now these are all ordinary differential equations of very familiar form, okay. So I'm sure that it is quite easy for us to write the corresponding general solution for each of these equations. Now this capital X, okay, as obviously is a function of x, the general solution for this equation is going to be a cos omega over c x plus b sine omega over c x. This is very similar to the general solution that we wrote for mx double dot plus kx equal to 0. When we wrote that general solution, we wrote this as a cos omega t omega nt plus b sine omega nt, isn't it? So because this equation could be converted into x double dot plus omega n square x equal to 0. Now omega n square is replaced here by omega by c square. So obviously, and the independent variable here is t, whereas here it is x. Okay. On similar lines, this particular function in time, capital T as a function of time, is can be written in a general solution as c cos omega t plus d sine omega t. Okay, so these are the two equations, two general solutions that we have for each of these individual functions. Both these functions are independently, these are two separate functions, one in time, one in x. So obviously, if these are the general solutions of these individual functions, then I can write the vibratory response of the stretched string, because this was written initially as through a separation of variables as t of t into x of x. So I'm going to rewrite this as the product of these solutions. So a cos omega by c x plus b sine omega by c x into the second function is going to be c cos omega t plus b sine omega t. Very simple and straightforward. That's basically the total solution of a stretched string as a function of x as a function of time. So you put a value of x and value of t at which you want to find the response. That is going to be the response, except that we still haven't figured out what these arbitrary constants a, b, c and d are. Okay, so we cannot get the exact response w at any point on the string at any instant of time unless we find out what these constants are. Now for this to be obtained, we apply boundary conditions, okay, so as to get all the very specific values of all the arbitrary constants. We look at what are the boundary conditions. Now what is the boundary condition for a string which is stretched at its ends? Okay, so what we are basically going to see that a string which is having a length equal to capital L, if it is stretched with a tension P in the string at the two extreme ends, what are the boundary conditions? Okay, so quite straightforward, that the string being fixed against any motion along the lateral direction at both the ends x equal to 0 and x equal to L, we write x at x equal to 0 at all times. The response in the lateral direction obviously is 0. Similarly, so this is one of the two boundary conditions. The other boundary condition, of course, is at x equal to L. At all times, the string being fixed at the other extreme end, the response is 0. Okay, so the string will vibrate in an arbitrary fashion. At all times, the response at these two fixed ends is obviously going to be 0. So these are the two boundary conditions we have. Okay, now let's substitute the first boundary condition here. If you look at the first boundary condition, the equation 1 becomes what? 0, because w at x equal to 0 is going to be 0. So this is our response at all times, and on the right side, when you substitute x equal to 0, this particular term is going to be 0. Okay, so you are left with a in the first term here, and the second term remains as it is. So it's a harmonic time function, c cos omega t and d sin omega t. That's the second term that remains as it is. Now if this is equal to 0 at all times, then a has to be 0, right? So the first constant is obtained equal to 0. Now if you now look at the equation number equation 1 from applying the boundary condition A. So applying boundary condition B, in equation 1 what you get, w at L comma t. So the left hand side is 0, that is how this boundary condition implies, and on the on the right hand side, since a is already 0, so you are left with b sine omega by c into L, that is our first bracketed quantity, and this one obviously remains as it is, plus d sine omega t. So that is how you apply the second boundary condition. You can notice that the x is replaced by L for substituting the second boundary condition B. Now again, if this is equal to 0, either this is equal to 0 or B is 0 or this term is 0. Now obviously for all times this cannot be 0, this bracketed term cannot be 0 at all times, and so the only thing that is left out for us is b into sine omega by c L equal to 0. Now b cannot be 0 because then you will have no vibrations. You can look at this particular term. If a and b both are 0, then that means the string is stationary, which is a sort of trivial solution we are not interested in. So for a non-trivial solution, we can say that b is not equal to 0, which ultimately leads to the condition that sine omega by c equal to 0. Okay, that is our now this is called as the frequency equation. This is just like our frequency equation which we discussed and saw in a 2 degree of freedom system or 3 degree of freedom system. We got frequency equation. So on similar lines, this is the frequency equation for a stretched string. Now this obviously means that omega by c into L is n pi, okay, where n takes the value from to infinity, and I would put a subscript here n, not the single degree of freedom natural frequency, but nth mode natural frequency. Now depending upon the value of n that you choose here, the integer, it will give you nth mode natural frequency. So I can write the natural frequency omega n for the stretched string as n pi c over capital L. So that basically is the natural frequency of stretched string. So if you want the first mode natural frequency, substitute n equal to 1. If you want 10th mode natural frequency, substitute n equal to 10. Now we already have seen that this string has been considered as a continuously distributed system, and obviously there are infinite number of inertia elements. In fact, we do not consider the inertia property to be discrete but continuous, and therefore instead of 1, 2, 10, 100, 1000 degrees of freedom, this is basically theoretically an infinite degree of freedom system, and therefore you can get as many number of natural frequencies as you want, right? Or in fact, theoretically or mathematically, you can see here that you can get infinite number of natural frequencies. So that is basically the natural frequency expression that you have got. Another very interesting part of this natural frequency expression that we should note is that your first or fundamental natural frequency is pi c over L. So omega 1 is pi c over L. What is the second natural frequency? Is 2 pi c over L. What is the third natural frequency? Is 3 pi c over L. So essentially the second natural frequency is an integer multiple of the fundamental, the first one. The third one is 3 times the fundamental, and so on. So the natural frequencies are integer multiples of the fundamental natural frequency. That is something which is an important interesting part of it. Generally for a vibratory system, they are not necessarily integer multiples of the fundamental. The higher mode natural frequency are generally not integer multiple of the fundamental. Here in a straight string that happens, and if you know the fundamental, you know the higher mode natural frequencies. Now I can now rewrite the response Wx comma t. So equation 1 I am now writing because I know the value of a and b. B of course is still an arbitrary constant, but sine omega by Cx, I have been able to get the frequency equation using the second boundary condition, but as a general solution I am still writing this as omega t plus d sine omega t. Now I can easily absorb this constant into these two constants, and then I can write this as sine omega by Cx. These are new constants. Instead of using some two different constant, you can presume that C actually is C into B. So cos omega t plus d sine omega t. Okay, so basically the constant B is accommodated in these two constants C and D. So C and D are basically new constants x comma t. That is basically the general solution that I have, wherein the constants a and b are already found. Now you can look at this function, which is completely a function in the spatial variable x, and this is completely a function in the variable time, okay, t. So you can view this as a mode shape. Okay, so the vibration is going to follow this mode shape, and so it basically means that the response at any point is a function of the position x, and as a function of time this is going to be harmonically changing. So the amplitude is given, so the maximum value of the translatory displacement, the lateral vibration of the string, is governed through this particular function, and that motion is going to be harmonically varying given by the second time function. Okay, so the bracketed second quantity is basically define the time variation of the response at any point. So the position, the sine omega by Cx will give you the maximum value at any particular point or position x, and that vibratory motion in terms of time will be governed by this harmonic time function. Okay, so this is quite similar to our multi-degree of freedom system, wherein we have written that to be composed of the mode shapes and the corresponding time functions. Now let us look at the mode shape. Now the mode shape, as I said, is given by sine omega by C into x. Omega n itself, you can see that if I want to now write the response in the nth mode, so I can write the response in the nth mode. Is going to be Wn x comma t, which is going to be the response in the nth mode as sine omega n by C into x, and of course you have C cos omega n t, and in fact I can write these two constants as Cn and this constant as Dn, sine omega nt. Okay. Now let's look at how the mode shape would look like. Okay, so let me show the how do we get a mode shape. Now the mode shape is governed by sine omega n by Cx. I can use the expression here to write omega n by C as equal to n pi by L, isn't it? So this mode shape is now going to be sine n y x by L. Okay, so that is basically the mode shape. Now what this value is for x equal to 0. Okay, so the value of sine n pi x, now let us suppose we are talking of the first mode. Okay, the first mode mean this n is equal to 1, so sine pi x by L will be the first mode shape. Okay, now when x is equal to 0, so when x is equal to 0, what is the value of this quantity sine pi x by L? This is obviously going to be 0. So the amplitude is going to be 0 at x equal to 0. Okay, what about x equal to L? So this is basically going to be sine 0, whereas this one is going to be sine, for the first mode, is going to be 1, sine pi, which is going to be 1, which is going to be 0, right? And so from sine 0 to sine pi, we all know that the function gets a maximum value at what? Pi by 2, which is going to be at L by 2. You can see that sine pi L by 2 upon L is going to be sine pi by 2, which is going to be 1. So if we treat this to be a one unit quantity, the value of the displacements at each of the x value gets pre-decided by the function sine n pi x by L for any mode. Okay, so the first mode is governed by sine pi x by L, and it basically encompass half sine wave. So this is the half sine wave for the first mode. So this is the first mode shape. What about the second mode? The second mode will be obviously given by sine 2 pi x by L, isn't it? Because the value of n is equal to 2, which means that at x equal to 0, this is again sine 0, and at x equal to L, what is this? Sine 2 pi, which of course is still 0, but we all know that sine pi, which is going to be the case when L is equal to x is equal to L by 2. So you can see that sine 2 pi at L by 2 is actually sine pi, which means that the amplitude at L by 2 is going to be 0 again, right? And we know that at L by 4 the amplitude is going to reach a value of plus 1, and you can notice that at 3L by 4 the amplitude is going to reach a value of minus 1, because sine 3 pi by 2 is going to be minus 1. So you can show the second mode to be following this particular sine function, okay, and this becomes now the second mode shape. Now the positions of the string where the displacement is 0 irrespective of time, so at all times when the displacements are 0, those positions on the string are called as the node points, okay. So node, we have discussed this node in terms of multi-degree of freedom system also. So the node positions are 0 displacement points at all times. So each position in the string do pass through 0 displacement position, but then at all times when the position on the string is having 0 displacement, those are the node positions. So the node position for the second mode is going to be 3 in numbers, but generally we can ignore the 2 fixed locations, and then the first mode is 0 node, the second mode is 1 node, and then if you look at the higher modes, you can see that each next mode is going to add up 1 more additional node point, okay. So it is left to you as an exercise to figure out what will be the mode shape for mode number 3. You will obviously figure out that it will add up 1 more node point, so you can show later on that the string is going to vibrate with this mode shape where these are the 2 node points and so on. So this is basically how the natural frequencies and the corresponding mode shapes are obtained, right, for a stretched string. The natural frequency, we should also not miss this point, that the natural frequency here is a function of what? When we say that it is n pi c over L, it obviously is a function of L, but we must not forget that it is a function of this parameter c, that is the wave speed, which has been already shown to be a function of the tension in the string and the linear density or the mass per unit length, which means that if you stretch it higher, that means if you stretch the string with a larger pulling force, then the natural frequency of that string, the fundamental natural frequency, will be higher, okay. In addition to that, if we have a thicker wire or mass per unit length is larger, that means you have a heavier wire, the natural frequency is going to be lower because rho appears in the denominator here, right, which is expected. A heavier wire will have a lower natural frequency, the mass being in the denominator here, right. So that is the reason why if a guitar player hears the sound of the string being plucked to be not commensurate with what is expected he finds that the tone is on the lower side, what he does is basically increase the tension in the wire so that the same pitch is obtained. So it's basically when you tighten those knobs, basically the tension is being increased. Okay, it's the same happens with a percussion instruments, musical instruments, where you essentially increase the tension to increase or raise the pitch of the sound or frequency of the sound. This is basically because the tension here is or the natural frequency here is directly proportional to the tension in the string. You might have seen the guitar player putting his thumb on the string. So when he puts the thumb on a stretched string, what basically is going to happen, so if this is the string which is stretched and fixed at the two ends, by pressing this thumb and pressing it against the board, what basically then is happening is that he's reducing the effective length of the string being plucked. Okay, so this is something which is going to cause again increase in the frequency. So if you want to play with the strings generating different the sounds of different pitch value, you basically start reducing the effective length of the string, and you can see that reducing the length of the string is going to again increase the natural frequency of the string. That you can try it out yourself, that if you have this instrument, you can see that if you plug the entire string, the natural frequency or the frequency of the sound is going to be of lower frequency, and when if you try to push this and restrain this part from vibrating so that the effective length of the string is reduced, you will feel an immediate change in the response. The frequency will increase. This is how these frequencies are dependent on the parameters of this vibratory system, the tension and the mass per unit length and the length of the wire. Now the reason for taking this particular string example is that most of our mechanical vibratory systems are just the extension or some advanced version of the governing equation that we have discussed for a stretched string. But before we go over to elements such as bar or a beam, we would continue a little bit more about how the free vibration response is obtained. This is just the response or free vibration response expression that we have got. So this is our free vibration response. We haven't still figured out what are these constants Cn and Dn. Okay, because these are still arbitrary constants. We have been able to only look at the expression for natural frequency of the stretched string, and of course about the mode shape expression, which is this. Again, you notice here that what we have obtained here is the nth mode vibration response, right? But it is not a complete vibration response. So it is quite obvious that the total response of the vibratory system is going to be summation of all the modes. All the modes will contribute to the total response of the stretched string. So Wx comma t is going to be summation of all the modes. So sine n pi x over L Cn cos omega n t plus Dn sin omega n t. Okay, now how do we find Cn and Dn? We obtain them from initial conditions, isn't it? Now this is quite similar to obtaining A and B from initial conditions of x and x dot. Just make a relation to a simple single degree of freedom system, wherein we obtained the the complete vibratory response by implementing the initial conditions x at t is equal to 0 and x dot at t is equal to 0. Okay, so what is our initial condition? W at any position along the length at time t is equal to 0 is your initial condition. So I will define this as W naught x. Okay, naught is this is basically indicating initial displacement, and because ours is a continuous system, initial displacement pertains to any position x. So the initial displacement of any point along the string is defined by this function W naught x. The second initial condition would be W dot x comma 0, which is at time t is equal to 0. What is the velocity value at each of the spatial position x of the string? So this I define as W naught dot x. Okay, so this is basically initial velocity at, so these at all positions x. Okay, x being a continuous variable. Okay, now how do we find this out? Before we do that, let's first get the time derivative of these of the total response, right? So we write W dot x comma t as a differential with respect to time n equal to 1 to infinity, and this being a function derivative with respect to time, this function remains as it is, n pi x over L, or better I use this omega n. Yeah, this is our original. We simplified it as n pi x by L. That is basically to get the mode shapes properly obtained. I mean, it becomes easier to get the mode shape by using that expression. But this is the standard way or standard expression for us. Omega n is the nth mode natural frequency, and the second term is basically, write this as minus omega n Cn sin omega n t plus omega n dn cos omega n t. So this is basically the velocity expression W dot x comma t. Now if we implement these initial conditions, the first condition gives me what? W naught x, which is by substituting t is equal to 0 in the first equation. Okay, so I get what? Summation n equal to 1 to infinity, at t is equal to 0, what do I have? Sine omega n x upon c Cn. Okay, and this equation, if I use the second boundary condition, which is this, I get W dot naught x equal to same, n equal to 1 to infinity sine omega n x by c, and of course the first term goes to 0, and then I have omega n dn. Okay, because t is equal to 0, this is what I am left with. All right, now these two terms essentially represent the Fourier series expansion of W naught x and W naught dot x. You remember Fourier series? You decompose that function into several harmonic functions. Okay, summation of all the harmonic functions. And if you recall how you obtained the coefficients there, way to get that is to multiply this function by sine omega n x by c and integrate it from 0 to L. Okay, and do that on both sides. So what I basically am doing is sine n equal to 1 to infinity, and okay, this is how you try to get the expression for Cn. Now it is straightforward. You might have done this while learning the Fourier series decomposition, that the product of this term and this term is 0 when you multiply the terms where the value of n is not the same. So for example, if you are trying to find out the Cn value for n equal to 1, only one term on the right hand side summation series is retained, right? So other terms are all going to be 0. So although you look at this product as again summation, where sine omega nx by L is getting multiplied to the sine term here. So if I choose n equal to 1, then Cn actually is equal to C1, and all the terms here are going to be 0 except one term, and in that case that term turns out to be L over 2, L by 2, so L by 2 into C1. You can show it yourself. This is a straightforward exercise in integrating, and then first integrating the product of two sine functions here, and you can show that when you multiply sine, let's say omega 1 x by c, with this series, which is going to be sine omega 1 x by c in plus sine omega 2 x by c plus sine omega 3 x by c plus, and all those terms into dx. So you can show that all the terms except this particular term is 0 when you integrate it from 0 to L, right? So that's how you get that the right hand side is this value, and the left hand side, which I will write here as 0 to L w naught x sine omega 1 x by c dx. Okay, and so I can write this C1 to be equal to 2 over L 0 to L w naught x sine omega 1 x by c dx. This is how I get the first coefficient C1. In general, you can write Cn to be 2 over L 0 to L w naught x sine omega n x by c dx. So this is how I get the first coefficient Cn. Following the same process, it is quite straightforward now for you to show that from this I can therefore similarly get the expression for dn, that's going to be 2 over omega n L integral 0 to L w naught dot x sine omega n by c into x dx. Okay, and that basically gives you the second coefficient dn. Once you have this Cn and dn calculated or obtained, this particular equation your total response is completely defined, because Cn is known, Dn is known, you have nothing to find. In that expression everything is completely known. You know what is omega n, you know what is Cn and Dn, and so you can find out the total response to any arbitrary initial excitation. Okay, so this is a free vibration response. You are basically trying to find out the vibratory response of the stretched string to certain initial condition. Now these are initial conditions that you are prescribing, right? So the value of Cn and Dn are essentially based on these kind of initial conditions that you have imposed on the stretched string at time t is equal to 0. Okay, now so this is already we have discussed, and you can look at all these mode shapes which are there, and we have already discussed how do we get these Cn and Dn values. In these expressions, of course, instead of omega n, I have used n pi x by L. That is again, so omega n by C has been appropriately replaced by n pi by L. So that is again an equivalent expression, but means the same thing. Okay. Okay. Now you must understand that this is again, if you compare it with a single degree of freedom system, what did we have? X of t was written as, let's say, a cos omega n t plus b sine omega n t, isn't it? That's the single degree of freedom general vibratory response. Then we substituted the initial conditions that at x equal to time t is equal to 0, this is x naught, and x dot at time t is equal to 0 is v naught, right? And you remember, you finally figured out that x of t is basically x naught cos omega n t plus v naught by omega n sine omega n t, and that's how the total vibratory response had been obtained in this particular form. So basically your Cn and Dn are obtained based on the initial displacement and initial velocity conditions that you impose, and so it is quite similar to our basic single degree of freedom's vibratory response. Okay. The only difference here is that you prescribe that initial conditions at all the x positions, right? So the initial condition in terms of w naught x and w naught dot x are going to be implemented or applied to every element of the string. It's not going to be discrete in that sense. So the summary of this lecture, we discussed today how a distributed parameter systems are modeled and how this approach is different in contrast to the lumped parameter models of the vibratory system. We also explored the vibrations of a stretched string, which actually is the simplest of the continuous systems, and through that discussion we got introduced to the distinctive character of a distributed parameter model of a given vibratory system. These are a couple of review questions based on today's lecture. And these are the corresponding answers.